Okay, what I'm going to do in this video is, we'll basically give an introduction to using Mathematica. But here I'm focusing on using Mathematica to solve finite element type problems or problems that we'll see in this class. If you haven't used Mathematica before, it's a very useful thing, especially when you have to do analytical type of work or derivational type of work. So what I'm going to do here is I'm going to go through the example problem I did in class. This is the discussion that's actually in chapter 1 of the cookbook of deriving the finite element interpolation, first in terms of beta and then the nodal unknowns and then the stresses and the strains and the stresses for the constant strain triangle. So we'll call this FEA Alright, so here I've opened up, this is on a Mac, but it's very similar in Windows. I've opened up a basic notebook. It has these little input portions of the workbook. They're kind of denoted with this weird looking carroty symbol here. Mathematica has its own sort of notation. For better or worse, they choose sometimes some odd symbols, but once you get used to it, it's quite powerful. So I'm just going to type in some text here. This does not intend to actually be functionally evaluated, so I can make that just regular text if I highlight this section. I do that by just sort of clicking on the cursor, and then I can go Format, Style, Title, and it makes it look like a title, or you can change it into something else. I forget what I usually use. I usually use section, I think. I don't know. But anyway. And then you can also put in little graphics. I'm not great at this, but we'll make a simple graphic here because, well, it's relatively easy. We'll just make the little triangle. So you can have little drawing tools, and we'll make a triangle. There's a triangle. I think I can stretch it. There you go. Move it around. Change it so the inside has a color. We can make it a little cyan looking color. And I think you can change the outline maybe? Stroke probably. Right. Make it blue. I guess something like that. Okay, so here's the constant strain triangle we're going to look at. I can put in some text here to denote the nodal unknowns. So this will be node 1. So we'll have a U1 and a V1 variable there. Also, we'll have one here. U2, V2, and then the third node up top. U3 and V3. All right. And I guess we also probably need the dimensions of the... I could probably draw a little fancy dimension arrows, but I'll just put on here dimension A, and then here we know the dimension is B. But I guess I could go back and draw more complicated stuff, but I'll let you fool around with that. And I think I can take the whole thing and make it a little more size appropriate. And then we can put in more text here, and this is basically, we'll just say, we're going to derive the finite element interpolation for the x and y displacement fields. For the constant strain triangle. Constant. Okay, this is just regular text, so we can just format this and make this style text, I think. It's just text. There's shortcuts to doing this stuff on a Mac. I usually hit the command symbol and then the function bar, and I'll do that. Okay, so the first thing we want to do is we're going to define the interpolation as a polynomial. Remember this we did last time. We looked at this element. There's in fact 6 nodal degrees of freedom, the u and v at 3 nodes, and that allows us to have 3 unknown terms. So we have 2 fields we have to interpolate, a u displacement, or the displacement of the x, and then the v, the displacement of the y. And so we'll do 3 on each, and that allows us to do a complete polynomial. So again, we'll make this text. And we will do we're going to define, now actually I'm typing in a mathematical function, u of h, and let me explain this. Well, this is probably well, actually, let's do it incorrectly first, and I'll show you why. Let's define the displacement in the x direction, u of h, and it's beta 1 plus beta 2x plus beta 3y. So I don't need these drawing tools anymore. You can see, actually, the kind of neat thing is there is, you have the ability to type in Greek letters, so we can put in like beta. You see here, I can put in a beta. Beta 1 plus beta 2 times x plus beta 3 times y. That's the displacement in the u direction, and then we can get the displacement in the v direction. And that's v of h, and that's beta 4, 5, and 6. Let me just, I had done some stuff earlier, so I'm going to actually kind of restart the kernel or the mathematical engine, because I have some stuff in memory, so let me just get rid of it. So I'm going to quit the kernel. It's actually a good thing to do every time you start a new notebook. So we'll quit the kernel, and then I'm going to restart the kernel. I should have done that before. It's thinking. And then we go to evaluation, start kernel. Now you can see actually all the variables are light blue. We can hit enter, and then we have this. Now, this is an expression, u of h, and this is what it's equal to. So it has an equality sign. Mathematica has 2 types of equality signs. This one is not a logical equality sign. It's an actual defining equality sign. So u of h is defined to be equal to this, and v of h is defined to be equal to this. Okay. Now, we want to solve for the betas in terms of the nodal unknowns. Now, to do that, we want to define the interpolation conditions. Interpolation conditions. So remember, there's 6 of them, because we have 2 fields. And the interpolation condition requires that if I put in the nodal coordinates for the node, say n1, the interpolation should yield u1 for the u displacement and v1 for the displacement in the y direction, okay? In fact, the interpolation should pass through the nodal unknowns. This is as opposed to a least squared regression or an approximation where it's not necessarily the case. So that's going to give us 6 equations that we'll be able to solve for the 6 unknowns. So the first condition equation, we'll call it condition 1, that's going to be equal to UH at 0, 0. That's this point. And that's logically going to equal the variable U1. Now this won't work, okay? And I'm going to explain why. It's kind of confused here. See, U of H, we look at this and we say, well, I want to put in x equal to 0 and y equal to 0. Mathematica has no way of understanding that this is in fact a function that we see in terms of x and y as opposed to a function in terms of beta 1, beta 2, and beta 3. All right, so this type of functional relationship doesn't really work the way we defined initially these guys. Okay, this is just an exact definition. we've also used this second equality here, because we're saying that this interpolation has to be logically equal to U1, so it's going to be able to solve that condition. Well, we need to fix this approximation so that it behaves like a function of x and y. And so the way we do that, again, this is kind of the weird looking Mathematica notation, is, and I'm going to do the same here, kind of rewrite these as follows. So I've done two things here. I've explicitly put square brackets to show the functional dependence of x and y, but I put a little underscore here to Mathematica does that. It's what's called a delay substitution. You don't have to worry about it too much now, but if you want to make an equation, a function that you're going to substitute in different things for x and y, this is the way you do it. And then the colon and the equal sign, again, delays this definition. So now if I redefine these as follows, okay, it didn't like it because I already defined it. So let me go back and restart the kernel. I wish there was a quicker way to. Yes, we want to quit, and then we're going to start it again. Now you can see these things are all undefined. If I hit enter, now it works. It doesn't show anything because this has delayed meaning. But now if I express this, here what it's done is it's substituted 0 for x and 0 for y into this expression, and it sets it logically equal to U1. So that just gives me, obviously, B1 equals to U1. I should have mentioned, I'm sorry, to evaluate an expression in Mathematica, I should have done this first. You hit Shift and Enter. Okay? So Shift and Enter. I should have been a little careful about that. Probably the best thing to do, if you've never used Mathematica before, is go to the Help, and then I think there is a Getting Started thing. Well, if you go to the Documentation Center, let's see, I believe there's like a 10 minutes to learn Mathematica or something like that. Getting Started videos. Go through those, okay? But they're pretty straightforward. But basically, you can use Shift and Enter to evaluate an expression. So here we'll evaluate this expression. Shift and Enter. All right, so we have other conditions. We can cut and paste. And now I can use return to put multiple expressions in one sort of command block. Let's do condition 2 is that the y displacement at node 1 has to equal the nodal unknown v1. And then we can kind of just copy and paste this for the other two nodes. So conditions 3 and 4 will be at node 2. Okay. So there, if we evaluate the interpolation at the coordinates of node 2, which is going to be x equal to a and y equal to 0, you should get u2 and v2 respectively. And then the last two conditions, 5 and 6, are at the third node, which is x equal to 0 and then y equal to v. And there, the u displacement should equal u3 and the y displacement should be v3. Okay? So these are the 6 interpolating conditions. Shift Enter, there they are. If you don't want to see what it evaluates to, you can put a semicolon at the end of everything. And now if I evaluate, you see it sort of dummies out the expression, but actually in this case it's nice to sort of see that. So there are the expressions. I can show you the order in which we're outputting stuff. Now, all right, so now in the interpolation conditions, now we can solve for the betas in terms of the nodal unknowns. Okay, so this is just a comment, so again, we'll format it to be text. Okay. Let's hope this doesn't crash. There it goes. So to do that, we need to solve these 6 equations for the 6 betas in terms of the u's, the other terms, the a and the b and the u's, okay? So the way we do that in Mathematica is this built-in solve function, square braces. First you put in the equations. It's actually a list of equations and then a list of unknowns we're solving for. If it's one equation, you just type in the equation and then the unknown. But here we have 6 equations. We're going to put them inside the curly braces. That's condition 1, condition 2, condition 3, condition 4, condition 5, and condition 6. We're going to solve for all those in terms of beta 1. And what you see here is there's actually a little shortcut. I forget exactly what it is in Windows, but in Mac there's a shortcut to actually getting the betas. But you can just click here too as well. We usually use the shortcut. In fact, I get kind of sick of typing everything over and over again, so I'll just copy and paste 4, 5, and 6. I can't solve. Oh, because I have an extra comma here. Wait, what's going on? Extra comma. 1, 2, 3, 4, 5, 6. There you go. So here's the solution. Beta 1 is U1, beta 2 is the minus the difference, beta 3 is minus the difference, beta 4 is V1, and this is the same stuff we got in class. So we're going to use the solution. I'm going to actually define it as solution, so I'm going to give it a name. Now I can refer to it. And for the betas. So now we can go back and take this solution and substitute it into this equation and see what we get. So we'll define U of H. I'm using a capital U to give it a different name. And this time I don't really have to go back and substitute in for x's, so I can do it as a functional definition, but let's just do it as a regular expression. So this is going to be little u of h evaluated at the general point x and y. Okay? So you can see if I just evaluate that, I just get this term in terms of x and y. But now I want to substitute in the solution. So it's a backslash and then a dot, and then you put in sol, and that'll take these solutions, and what it'll do is everywhere it sees beta 1, it'll put in U2, everywhere it sees beta 2, it'll put in this expression, so on and so forth. And you can see that's what you get. Puts in a little list because this is a list. If you want to get rid of the list, the curly brace, you can actually identify the first one, and it'll get rid of the curly brackets. But that really doesn't matter, okay? So now we're going to get of the nodal unknowns. Okay. There they are. And we can do the same for the y displacement. We'll call it capital V, and of course now we have to use lowercase VH, puts in the solution, and that's what you get. There's that linear field, okay? All right. Now we can get the strains. Okay. Let's compute the strain field. And so to do that, the normal strain in the x direction is the derivative. And to do a derivative in Mathematica, use this capital D operator in square brackets. The first argument you put in is the expression you want to take the derivative of. In this case, it's the displacement in the x direction, right? Remember the strain in the x direction, the normal strain is the derivative of u with respect to x. So here we're taking the derivative of this expression with respect to x. And that's what you get. And we can do a cut and paste. You get the normal strain in the y direction. That would be the partial derivative of the displacement in the y direction with respect to y. And we could also get the the shear strain. This is the tensorial component, not the engineering one. And we can get that as 1/2 the sum of the derivative of u with respect to y plus the derivative of the y displacement with respect to x. And there they are. Those are the strain fields. And again, you can recognize they're in fact constant, okay? So now what we can do is we can go back, in fact, and we can solve for other triangles, okay? So this is kind of a neat thing about it. This is an easy problem to do in class. It's easy to do by hand. But actually we can modify this a little bit if we want to allow for some other coordinates, okay? Let's say we wanted to do it where, in fact, the element that's sort of upside down. In this case, node 1 would be at the coordinate A0, node 2 would be at the coordinate AB, and node 3 would be at the coordinate 0b. So we can kind of put those things in. Actually, if you want to cheat a little bit, we can actually put in the coordinates here as an unknown. These are interpolation conditions. We can actually put them before here. We can say, define the nodal coordinates to make it more general. So I can say x1 equals 0, y1 equals 0, x2 equals a, y2 equals 0. I'm actually just putting in the coordinates of the nodes as drawn here. x3 equals 0, and then y3 equals b. So those are the coordinates, and I can actually go back here and put in x1, y1. Those are the coordinates of the first node. For the second node, and then the third node. So you can see actually what I've done here, this is the same thing that we did before. We're solving the same exact problem. There's no difference. The only thing we've changed here is we've added this flexibility that I can redefine the nodal coordinates relatively easily. So let's evaluate that. And you can see here are the conditions. You can see I get, oops, well, it's already put those back. Yeah, it gives me the same exact equations. In fact, if I go through and solve everything again, you can see you get the same solution. Okay? Everything stays the same. Because it's just substituted in here. Now, we could change it, though. Let's use the triangle that's sort of its upper neighbor, where this would be node 1, node 2, and node 3. So node 1 has the coordinates A0. Node 2 has the coordinates of AB. And then node 3 would have the coordinates of 0b. Now we can go through. Now the expressions will change, okay? And then the solution will change as well. And you can look at the approximations for that element. That also has changed. It's still linear, but it has changed values. That's because it's a different configuration. And then likewise, we get the strain fields, and again, that changes. Still constant, but it has different values because it's a different functionality of the variables. Okay, and as we pointed out in class, you can see obviously the strain is constant in the element, and it will not be continuous across the element. So there'll be one strain value here and another strain value in this element, okay? So it's discontinuous. All right, so if you're not in my class and you're looking at this video, you might be a little lost as to what I'm doing because I explained this in the lecture, but if you went to the lecture, you should be able to fill in those blanks. If not, it's we're using the book by Robert Cook, Finite Element Modeling for Stress Analysis, and this is basically what's discussed in Chapter 1. Okay? So, as I said before, mathematics is really easy to use. There's those problems like 5 and 3 where you're using different configurations and you're doing the same thing over and over again. So actually you can do something like Mathematica quite easily to get the answers, okay? All right. Thanks.